So this implies that gamma 1 is equal to 0. Right?
So over there, in the first step, we are splitting xi into x1 and x2.
Yeah, because x1, x2 are two values of x.
So we don't do the same in the denominator.
Where?
In the denominator.
Here?
Xi square in the above step. Yeah, exactly.
No, you can keep it like this because it's going to be convenient for the later sums. So it won't matter if you did that, but that will not give you any additional advantage. So keep it like this. So if you do this, what you get from here is, I'll just answer Harsh's question in a second now. So what this means is, this can mean summation. So variance of beta hat OLS. Yeah? Now I can take summation xi square, sigma square out common. So this then becomes, right? This then becomes sigma square upon summation xi square. Right? Or to write this more interestingly, yeah? It's the same thing. But now xi is actually xi minus x bar. Right? But realize xi is actually equal to xi minus x bar. So what is this quantity? Summation xi minus x bar square upon n. What is that? Variance of x. So this can be written as, yeah, that is the variance of beta hat. Now, what do you mean by the variance of beta hat? Intuitively, what do you mean by the variance of beta hat? Assuming that x and e are uncorrelated, what do you mean by the variance of beta hat?
The average difference of beta hat around beta.
Average difference of beta hat around beta. Right? So, what is more preferred? A larger variance or a smaller variance? Smaller. So, smaller variance meaning that your beta hat is more accurate. Now, this is telling you, therefore, variance of beta hat is nothing but the reciprocal of the accuracy of beta hat. Larger the variance, smaller the accuracy of beta hat. Larger the variance of beta hat, smaller is the accuracy of beta hat. Smaller is the variance of beta hat, greater is the accuracy of beta hat, because all values of beta hat are now closer to beta. Right? Okay. So this formula therefore is very important from a statistical modeling point of view. It says what does the accuracy of beta hat depend upon? Look here, first, alpha. So I'm not using an intersection. Let me keep to that state. Yi. So what are the sources of variation in y? Why does y move? X or e? Right. What are we interested in measuring? We are interested in measuring the change in y per unit change in x. Now suppose x is not changing at all, but y keeps on changing because e keeps on changing. So for example, if x is the distance from Churchgate station to Karina campus every day, right? And y is the time it takes you to come from Churchgate station to Karina campus every day. Does x change on a day-to-day basis? X is the same, no? Does y change? Yes, because it is y is equal to some beta x plus e. Right, where beta x is the average time it should take on any given day. The actual y is this average time plus or minus some random shot. And all the variation is because of the e. Right. Now given this, can you ever say how much time will it take you, how much more time will it take you to come to Karina campus if Churchgate station were to be shifted 1 kilometer further up? Can you answer this from this data? No, because your Churchgate station in all your data has been where it is, so there is no variation in x, no? Yeah? Or look at it this way. Suppose you are looking at household, you are trying to understand relation between household income and household expenditure. Now you study all households which have the same identical income. Their expenditures will vary. On that basis, on that data, will you ever be able to say how much does the expenditure increase if income increases by 1 unit? You will not be able to say that because your data will simply not have that information. Right? So if the variance of x is 0, if the variance of x is 0, the variance of beta hat will be undefined. Which is another way of saying that if there is no information in x, right, you can't estimate y at all, you can't estimate beta hat at all, and therefore you cannot say anything about its accuracy. Now suppose you studied 100 households, 99 of them had the same income, and one household had a different income. Then you will be able to say something about how y changes with x. But that will depend upon that one particular household that is different from others. No? And you could have picked up any other household. So your estimates will be quite unreliable. The variance of your estimates will be large because the sigma square x will be small. So what it says is, if you want to minimize the variance of beta hat, what you must do is minimize sigma square, the variance of the error term. Maximize the variance of x. And maximize n, the number of observations. Right? So a good, reliable estimate of beta hat requires 3 things. One, it requires a large sigma square x relative to sigma square and a relatively large n. Okay? Larger the n, the more accurate is the estimate of beta hat. Larger the variance of x relative to the variance of the error term, larger is the accuracy of beta hat. Larger is the accuracy of beta hat. Is this clear, folks? Right? Okay. So now tell me one thing. Suppose I have a model. Okay. Suppose I have a model where yi is equal to beta xi plus gamma zi plus ei. So y depends upon x and z. And suppose x and z are not correlated. Suppose x and z are independent processes. Okay, suppose x and z are independent processes. Okay? Alright? Sure. Now, suppose you do not have data on z, or for some reason you neglect z in the regression equation, and you run the model where vi is the error term of the new model. Yeah? Vi is the error term of the new model. What do you think will be the consequence? The error ei, so vi will now be this whole thing. But will it be, will the ONS estimator go biased? No, because vi and xi is not correlated. Vi and xi are not correlated because we have assumed z and xi are independent. If z and xi are independent, the omitted variable bias is not there. The omitted variable bias comes if you drop that variable, then the error, which is correlated with the included variable, then x and e get correlated. So the omitted variable bias is not there. But what is the problem? Then what will happen? So omitted variable bias नहीं है, मैं z को drop करता हूँ, मेरे पास data नहीं है z पे, or that I just didn't realize that is there.
So because vi also consists of zi, it might not be a consistent estimator.
So what will be the variance of vi? Variance of vi will be the variance of vi plus gamma square variance of zi. Right? So in the numerator here, you will just not have sigma square. You will have sigma square plus gamma square variance of z. Yeah? So the numerator and fractions become bigger and the reliability of beta hat will go down. Yeah, so you remember, please remember one thing, in a regression model, more havoc is caused by variables which are not there than by those that are there. Right? Variables cause problems by their absence, not by their presence. Yeah, not generally by their presence. Because what would happen here? Either that variable is correlated with x, in which case your regression model has gone for a toss, or if it is not correlated with x, the estimate of the coefficient of x is being affected. Yeah, for example, if the household expenditure, consumption expenditure of a family depends upon, say, the income of the family and whether there have been some birthdays in that family in that one particular month. Suppose you collected data like that. Now, Xi is the income of the family, Zi is the birthdays in the family. Whether that family has a birthday in that particular month doesn't depend upon that family's income. It just shows 1 month to study. So Xi and Zi are independent. But if you don't take birthdays into account, then what it says is the coefficient of income which you have included in the variable will be unbiased and consistent, all right, but it will be quite inaccurate. It will be quite inaccurate because in the numerator you will get the additional term gamma square z square, variance of z. Gamma square variance of z will come in the numerator of the variance of beta hat OLS. Variance of beta hat will be now sigma square plus gamma square sigma square z upon n sigma square x. You see the point? Yeah? Sure, so if you drop a variable, then that variable at the least worst can actually make your beta hat estimates unbiased, and at its worst make your beta hat estimates quite inaccurate, and at its worst can actually make them biased. You see the point? Therefore, we have to be very careful about what are the variables that we have to include in a regression model and make sure that all the important variables are included. Okay, in the last class we talked about endogeneity coming from the errors of measurement in X. What do you think will be the impact of errors in measurement of Y? So your regression model is yi is equal to beta xi plus ei, but you measure yi star, which is yi plus say some vi. Alright, so instead of there being errors in measurement in X, we have talked about this, right? So if there are errors in measurement in Y, what would happen? Think through the issue.
Beta hat will not be consistent.
Why will beta hat not be consistent?
Because covariance xi, yi will include an error term di.
Let's write this. Okay. So I have on this side, I have yi star minus vi is equal to, yeah, or I have yi star is equal to beta xi plus vi plus v. And let me assume that the errors in measurement in y have nothing to do with x. Okay, errors in measurement of y have nothing to do with x. Like for example, I tried to see whether your IQ depended upon some training which I have given. Why is your measured IQ? Your measured IQ is different from the actual IQ. Right? All of you would like to claim that the actual underestimates your, the measured underestimates your actual. But you know, that's like everybody would like to say. Like everybody in the world believes that they are better than the average driver. I don't know how everybody simultaneously can be better than the average driver, right? But that's what everybody believes, right? So if your actual IQ, so yi could be your actual IQ, and xi is the number of hours that you have put in for doing some mental exercises. I can't measure your actual IQ, so I do a test and I do y star. Y star is equal to, I measure IQ with an error. But that error has nothing to do with the number of hours that you have put in for studying, because that error is a result of my institute, not of the number of hours that you have studied. So Vi and Xi are uncorrelated, Vi and Ei are also uncorrelated. In which case, what is going to happen to the regression? So will there be an omitted, will there be inconsistency, unbiased, or will there be a bias, will there be beta hat OLS, will it be biased or unbiased? Yeah? What do you guys think? Will it be biased or unbiased? So I can call, I'll get a new error term here, no? I'll call it say eta I. Y star is equal to beta xi plus eta I. Eta is normally distributed and all, right? And eta and xi are not correlated. So with the OLS estimated from this model be unbiased and consistent. What do you guys think? Say something. Should be unbiased. Okay. Should be nahi hote hai. Will it be or not be? Don't sit on the fence. When is an OLS estimator unbiased and consistent? When X and E are uncorrelated. Here is X and eta uncorrelated? Yes. So beta is an unbiased estimator. So problem नहीं है जो when you have measure errors in measurement in the x variable जो problem होता है, that problem is not there when there are errors in measurement in the y variable.
So is Yi and Bi correlated or uncorrelated?
Which one?
Yi and Bi.
Of course, no. Yi is independent of Vi, no. Vi is the measurement error. Yi is your actual IQ. Why should your actual IQ be correlated with the measurement error? No. Right? Okay. So Ei plus Vi eta. But then what is the problem? Then the variance of, so what will be the variance of beta hat OLS in this case? Variance of eta I upon n sigma square x. What will be variance of eta I? Variance of Vi plus variance of Vi. So it will be too large. So the variance, therefore beta hat will become imprecise. So if your y variables are measured with error, your beta hat is imprecise. If your x variables are measured with error, you can't calculate beta hat. Yeah? You can't calculate beta hat. Sure? So, if you think that y is measured with error in your data, suppose if you think that, of course I am measuring people's IQs, but those IQs are likely to be measured with error, right? And that error is likely to have a fairly decent variance. So, what should I do? What should be my solution to this problem? So as a designer, somebody who is making a regression model, who is deciding to do this regression model, and then deciding to collect data, so your first step is to increase n. Okay. Increase n. So have as large number of data points as possible, and secondly increase sigma square x. So look at students across the intelligence spectrum. Right? So you can have some very bright people like some of you, some very dull people like me, and then you will get a large variance, right? Compared to if you have everybody just like me, right? So basically you'll have to spread out and make sure that your sigma square x is as large as possible, right? So you will include everybody in the spectrum of intelligences. Yeah? No. Sigma square x is the average sum of square deviation. So sigma square x can be constant, but you know, it is what? Summation xm and x bar square upon n. So it doesn't necessarily increase with n.
So but by increasing n, aren't we indirectly increasing sigma square?
But you are not increasing sigma summation xm and x bar square upon n.
No, so not that, the numerator.
No, the numerator is the variance of the error term. It's the variance of the error term, which is sigma square, which is a constant.
And that we assume to be constant, the variance we assume to be...
Because it's the error term, so what is sigma square? Variance of the error term, it's come, the error term has a particular distribution. It has a mean 0 and a variance, some sigma square. Right, so you don't increase the variance of the error term with the sample size. In fact, that's a constant number. Yeah? So you see how this equation is important? Okay. The next step this equation leads me to is, so I now know for example, instead of writing this, I now know or sure, which implies is a standard normal, right? Which implies a standard normal. So if you find, suppose I tell you that sigma square is equal to 1. Suppose I tell you is equal to 16. If I tell you that beta is equal to 0.3, what is beta at? One particular value of the estimate that you have. But are you interested in that one particular beta? No, you're interested in expectation beta. What is the value that I would get if I did many such things and averaged them out? That would be expectation beta. You can't actually calculate expectation beta hat, but you can definitely test the null that beta is equal to 0 against the alternative beta is not equal to 0. For example, what would that be? In this test, you write 0.3 minus 0 upon the square root of 1 upon 60. And in this value, you can use say minus 1.96 plus 1.96, for example, constant intervals, and then decide to reject or fail to reject the null hypothesis. Yeah? You can reject or fail to reject the null hypothesis. Right, so you can actually do, this formula is important because it allows you to do actual hypothesis testing on it. Now, again, I will point you to the variance, importance of the variance of beta. If the variance of beta is too large, what's going to happen? If the variance of beta is large, that fraction is going to be small, no? The z value is going to be small. So the chance that it lies between minus 1.96 plus 1.96 is going to be large. So you are actually, you will end up in a situation where you cannot reject the null hypothesis, not because the null hypothesis is true, but because your variance of beta is too large, your beta estimate is too inaccurate. Yeah, because your variance of beta is too inaccurate. Right? Sure? Okay, so therefore if you have a small number of observations, you will end up failing to reject a lot of null hypotheses, which is called type 2 error. Type 2 error in statistics is the probability with which you fail to reject the wrong null hypothesis. Type 2 error is the probability with which you fail to reject the wrong null hypothesis. And the probability with which you reject the null hypothesis which is wrong is called the power of the test. The probability with which you reject the wrong null hypothesis is called the power of the test. So obviously the highest power of a test can be 1, the lowest can be 0. A test with power 1 always rejects the wrong null hypothesis. A test with power 0 never rejects the wrong null hypothesis. The larger the power of the test, the better. Now here it means that the variance of beta is large, the power of the test will be low. The power of the test will be low, right? The power of the test will be low. Is this clear? Sure, so if the n is large, n is small, or sigma square x is small, sigma square e is large, then the power of the test is low. Right? So therefore, setting up a good econometric model requires you to ensure that the test that you are going to use has the maximum power, have as high power as possible, and which means that your chances of n sigma square, whether your y variables are measured with error, are measured without error, if you have dropped out some important explanatory variables, all these issues become important from the perspective of the power of things. Right? Okay, folks? Now let me look at the instrumental variable. Okay, we know that the instrumental variable is also normally distributed. Its mean will be beta. It's unbiased. Right? Let us see what the variance of the instrumental variable is. Okay. So now, let me write the variance of the instrumental variable.